Hello, good day. So we're now about to start with the next part of our discussion for the IC circuits, specifically the 555 timer. So for today, we were supposed to do some examples for some design problems involving 555 timers, but after a while, I thought that I need to explain first the design conditions for a 555 timer. Remember when we talked about multivibrators last week, we divided them into three. We have the astable, the bistable, and the monostable multivibrator. So, being the 555 timer, sorry, being the most common timer used in most digital circuits, we'll be using the 555 timer and design it in such a way that will be able to create all three types of multivibrators. So right now I am using Multisim. This is an online uh, circuit simulator in which you are able to put in several devices, then test output and inputs, just like using a normal multimeter, a frequency spectrum analyzer, and or an oscilloscope. So this is totally free. So just go to multisim.com. You just put in or sign up, and then you'll be able to use their free multisim circuit simulator. Anyways, I am now on an untitled circuit, and I'll be trying to create first a monostable multivibrator. As mentioned, a monostable multivibrator would shift to a specific level, either high or low, stays there for a specific duration, then goes back to its stable state. So as mentioned, it only has one stable state. The other state is unstable. Once you go to that unstable state, after a fixed duration, it will go back to its stable state. So first and foremost, we of course need a 555 timer. So one of the things that we do for multisim, most of the common devices can be found here. Like the first one is used for measuring or for capturing data. So it includes voltage and current, um, probes, if you will. We also have the ground, and some schematic connectors, the passive devices, which includes resistors, capacitors, inductors, etc. We have different voltage and current sources, different types of diodes, transistors, some indicators like lamp, LEDs, 8 LED bars or a buzzer, switches, and other things that you might be needing in order to create a simple simulation of a simple circuit. So this time around, I'll be needing a 555 timer. In order to do that, it's not, I don't think it's in on one of the blocks. So I'll just search for 555, and it will result at a 555 timer. Then I just click, and then click again. So it's not drag and drop. It's just a single click, then click on where you want to put it. Now I'll be zooming in using my mouse wheel rather. The pinouts are arranged according to, or they are labeled according to their use. So it's not arranged how they are actually physically connected or physically placed on the IC, but how the pins shown here shows the specific name of the pinouts. So we have the VCC, the voltage source, the output, the reset, discharge, the threshold, the trigger, the control, and the ground. So in order to create a monostable multivibrator, so let's connect the VCC first. That will be our source supply. So we'll be getting it from here. We'll be needing a DC voltage. 555 timers usually can work from about 5 to 15 volts. But for now, we'll be using 15 volts as our reference voltage because that's the most commonly used voltage source for uh, digital logic. So then next we'll be putting in a oops. Let me change the voltage. Changing the voltage is just clicking here, or you can click the voltage itself, then change it, or you could click here, then click on where's that? No, rotate, delete. Oh no, that's the duplicate. So I guess you click here. So we change this to 5 volts. You can put in 5, or you could drag this along. Okay. Okay. So I'll be putting in my wires first. So it's just clicking we just have to click on one of the terminals. Then this is it's not drag and drop, it's click, then move. So I'm not dragging, I'm actually clicking. When I want to create a junction, I click again. Then I click to the endpoint. Remember, I have to put in the VCC here. The number 1 here represents the node, or the number of the node. Because there's a connection between the VCC and the terminal, this acts, or this is named as node number 1. So that was useful in some of the um, connections or analysis. I'll also be connecting this to the ground as well. Well, the ground represents the negative part of voltage, but in most cases, they actually connect it to a literal schematic symbol for the ground for reference purposes. It's named 0 because the ground is always referenced as node number 0, where the voltage difference is 0. For the output, normally for 555 timers, they use an LED to indicate high and low digital levels. So that will be the one that we'll be using here. So we'll be using an LED. In most cases, when we're going to build a circuit, we don't directly connect the LED, but rather we put in a limiting resistor of around 1K, sometimes 300 ohms, just to make sure that the current being drained by the LED won't actually destroy it, because that happens in most cases. Then we connect it to the ground as well. Okay. Now next, what do we do with the reset, the discharge, threshold, trigger, and control? For reset, as we won't be using the reset button for the monostable, or at least for this configuration, we will be connecting it to our VCC. Remember, the reset, and most of these pin outs are actually active low, or they activate if a low level signal, or if they detect a transition from high to low, or a falling edge. So we'll be connecting the reset to our VCC to avoid resetting the 555 timer. Okay, there we go. Then as for the discharge and threshold, we'll be connecting it to a resistor. So I'm going to rotate it, Shift R, okay, to rotate. And I'm going to put in 47 kilo ohms for now. The resistance that we're going to put here, the resistor we're going to put here, actually has an effect on the output. I'll explain it later. So I'll be connecting it to our VCC first, or node 1. Then my 47 kilo ohm, the other terminal will be connected to the discharge and the threshold as well. So they only have one connection. Now I'll be connecting R1 to a capacitor. So let's go to the passive devices, capacitor, then Shift R to rotate, place it here, drag and drop, then connect it to the one end to the ground, and one end to our resistor or node 3. I'll be giving this a 10 microfarad. I'll explain the values later, and we'll be seeing the effects as well. We'll be needing another resistor, capacitor. We can duplicate this and just put it, I know, here, and put a wire node 4 and node 0. We'll be just putting in a very small value here, 10 nanofarad. The control here, or the control pin, connected to a capacitor, is actually used just to make sure that our circuit is not affected by fluctuations in the circuit. So the 10 nanofarad acts like a filter. Remember when we had built our power supply, we connected a capacitor at the end, which now features a which acts as a simple filter for our output. So instead of pulsating DC, we have a instead of ripples, we have small ripples for our DC voltage. So that will be C2 and then 10 nanofarad. We use a very small percentage such that it would filter out the fluctuations quite well. Okay. Now, as for the trigger, we'll be needing another resistor. Unlike the value here for R2 that we'll be using for connection, we connect it to the trigger. Trigger is also active low, so that means it would activate, or you're going to activate the trigger if it is in the low position or there's a falling edge, a transition from high to low. So right now we're connecting it directly to the VCC, so it's in 5 volts. So in order to create a sort of connection, or to make it, or to activate it, we need to be able to shift it from 0 or from high to low. So we will be needing a switch. In this case, we'll be using an SPST, or single pole, single throw. Rotate it. Don't like the rotation. Let's put the switch on the other side here. Okay. Connect it. And then connecting it to the ground. What would happen is that when I switch this on, instead of the trigger getting voltage from the VCC, it would actually become equal to 0. So it would have a transition from high to low, and that high to low transition actually triggers our 555 timer, activates the trigger for the 555 timer. Let's turn this off again. Okay, so what's the reason for connecting it such as this? So let's split this first, because we can have, this is a schematic view, we have the graph view, and we have the split view. So I like the split view better, but I forgot something. Let's put voltage markers on the LED, another voltage marker for the switch, and another voltage marker for the capacitor here. Let me put that somewhere there. Let's try to turn it on. Hopefully it works. So right now it's running, but one of the good thing about the simulator is it won't start graphing unless I click the switch. So once I click the switch, then turn it off again. Let me drag the switch here. Okay, so it goes down. So let me pause that. So the green here represents the LED. Okay? So it turned on, so it was actually initially off. It didn't start calculating the voltage prior to the switch, but actually once I turned on the switch. Once I turned on the switch, the trigger, so the voltage here, this one, light blue, goes from 5 volts to 0 because it is now connected directly to the ground, which activates the trigger. Activating the trigger now allows the LED to light up, but it also turns on the discharge, or actually turned off the discharge. What the discharge does is that, as the name suggests, is that in this specific circuit, the 5 volts is actually discharged through the discharge pin. So instead of being collected by the capacitor, remember the capacitor usually charge a specific electrical charge depending on the capacitance and the amount of current flowing. But instead of flowing through C1, it actually flows to the discharge button and down to the ground. Now, once I turn off the switch, it turns on the LED light and it turns off the discharge. So it means that instead of the current flowing from the resistor then to the discharge, it actually flows from R1 to C1. So this acts like an open circuit. So what does that mean is that the C1 would now start to charge. Okay? So that is what we see here in the dark blue line. Now, how long would it charge? It would charge and it would stop once it reaches 2/3 of the supply, which is 5 volts. The 2/3 of 5 volts would be around 3.33. So you'll see that around here at 3.33 volts, it actually stopped charging and it discharged all of its contents. Why? What happened? Inside the 555 timer, as we mentioned before, there are actually two comparators there. The comparators used there is used to control the flip-flop, which controls the output and other things, especially the discharge. So what happens is that once it reaches the 2/3 voltage, it deactivates the output. It resets the flip-flop inside, giving an output of 0. Besides that, it also activates the discharge, meaning the open circuit here is now a short circuit. So that means all of the current here would now flow and be discharged to pin 3, which is the discharge button or the discharge pin, and down to the ground. So you will see here an eventual flow. Let's try to turn it on again. I'll play it again. So right now it does nothing. I'll turn this on. As you'll notice, it's red here because it's turned on. I turn it off again, so it goes back. But it would go back, as you see, once it reaches 3.33, it would go down. Together with the LED, it turned off. The one that triggers the LED from lighting up is not how long I press S1, but the moment of instance that it was pressed. So it really doesn't matter how long you press it. As long as you pressed it, it would activate. The only thing that you have to consider is that you don't want to press it for quite a while or until it discharges. Let's try pressing it and not unpress it or turn it off. So it would still go normally. LEDs light up. Trigger is triggered. But once it reaches 1.3, it goes bonkers. Like that. So it oscillates from 0 to 1. Okay. Like that. And that messes things up. Okay. In reality, when you do this physically, you would see the LED is still lit up. As it oscillates quite fast, you won't see it blink. But we have to turn this off in order for it to return to its stable state. Again, its stable state is 0. And its unstable state is 1. Now, Going back to what we have here, as you can see, the duration for how long it takes it to go to its stable state, or the duration of the unstable state, is actually constant. And it is controlled by both R1 and C1. So let's see what happens if we have C1. So from 10, we bring it to 5. So we play it again. So it's going to resimulate. I'll turn this on, okay, and turn it off again. It still reaches 1.33, but instead of, we forgot to actually take a look, no, how long it takes for the 10. So let's stop this first. As a point of comparison, I'll turn this back to 10 microfarad. I'll play it again. It's going to simulate again. Let's check how long it takes for it to charge and discharge. So it's charging. How long would it take it to reach 3.3? Remember, when it reaches 3.3, the LED will turn off. So it reaches a point of 514.84 milliseconds, or almost 500 milliseconds. So let's turn this to 5. Then play it again. So turn on and off for it to start charging and discharging. So it actually goes high quite fast, and it goes down at around 257.95, which is half of the duration of the unstable state for 10 microfarad. So dividing the capacitance by 2 actually divides the duration by 2 as well. So of course we could double it, make it 20, but you might have already guessed what would happen. But let's confirm. So let's play it again. I'm gonna turn on and off our switch. So it actually rises quite slowly compared to the other one. You'll see here how it rises up to 3.33. At 3.33, you should expect it to stop. It's still 5 volts. This is around 5 volts. Oh, there we go. So around 3.33, that would be around 1.0318 seconds, or twice of the 514 milliseconds that we had a while ago. So that means that the capacitance is directly proportional to the duration of the unstable state. Doubling it, having it, would have the same effect on the duration. And the same is true with our resistor, because it's not just the capacitor that has an effect on the duration. So if we have 47, we choose 47 because that's the, if we combine 47K with 10 microfarad, that would give us approximately a 500 millisecond unstable state. Okay? Having an exact 500 millisecond unstable state would be quite hard, as the values needed for both resistors and capacitors would be unavailable. Remember that their values are only available at discrete amounts. So let's double this to around 100K. There we go, 100K. And let's play this again. Now, if this has the same effect as the capacitor, then this should be around 1 second as well. A 1 second unstable state. By the way, the duration here is not real time. Yeah? So you might be thinking, 1 second, why is it taking so long? No, it's not like that. As this is a simulation, and it's actually quite better for us to see it this way. So it's a slow-mo for some reason. Okay? So after 1.09 seconds, or twice of what 47K is, or almost twice what 47K is, then it is our duration. Okay. So we could expect that if we have this, it would also have. Okay. So let's now try creating the bistable state. Technically speaking, it's easier to create a bistable multivibrator than a um, monostable multivibrator. So we'll be deleting some of this here. Let's delete this and this. Okay. And this and this and this. Let's delete this first. So what we're going to do is we're going to use the reset and the trigger button as trigger pin as our um, main pinouts. Okay, so um, the resistance here actually does not affect the time of the, because they have two stable states. That means the duration is indefinite as long as you don't trigger it again. So let's duplicate this. The amount here is actually for how large the current will be flowing. So if you want to protect your circuits and your passive elements, you want to have a higher current, but you don't want a small current that it won't drive your ICs, or it won't turn them on or activate for some reason. So one of them will be connecting to the reset. One would be for the trigger. The discharge and threshold won't be used for this one. We'll be needing a different switch. We'll be using an SPDT. So what we'll be doing is that, remember that both trigger and reset are both active low. Okay, so the active low state would be okay. So we'll be looking into connecting it and then connect it to the ground. So we won't be activating both of them at the same time. We're just activating either. If right now it is activating the trigger. If we press this, it will be activating the reset, and that's it. We don't need a capacitor, as we don't need a duration for it to charge and discharge. Still need the control to connect it with the capacitor to control the fluctuations in the voltage. Okay. So let's try putting a voltage here, voltage probe here. Let's split it again and try pressing play. So right now it has activated, it's turned on. Okay. The blue indicates reset because it is directly connected to the VCC. It's at 5 volts. The trigger, which is light blue, is at 0. Where's the green? The green is actually here as well because the blue is I'll raise this up a bit. The green is also here. It's also 5 volts, as you can see here. Okay. So I'll be pressing the button here and check what happens. After pressing this, now the reset has a direct connection to the ground, and the trigger now has a connection to the VCC. So the one that is activated is the reset. That's why the LED is now 0. Okay. And if we want to turn it on again or put it a high output, we switch it again. So there are two stable states. Stable states being that the output doesn't have a duration. You actually have full control if it's 1 or 0. So we can play around with this. And it actually has two stable states. So no calculations or no amount of computations needed, as there is no duration, that we don't need any duration to compute or calculate. Again, the resistors here, the value of the resistors here is needed to um, limit the current. So if we put in a too little resistance here, it might have a large current that might destroy here. So we need to have a balance between small and large current. Because if the current is too big, it would actually if the resistance is too big here, the current would be too small to actually drive or activate our 555 timer. Now let's now try creating an astable multivibrator. So we'll go back to our schematic. We're going to get rid of this again, the switch. We won't be needing a switch this time. So we will be connecting, we'll be needing two resistance here. And another resistor here. So let's put this in 47 kilo ohm. Let's have them both at 47 kilo ohm. I connected the reset to the resistor and VCC. So instead of connecting the discharge with the threshold, I'll be connecting the discharge to the 47K, its other output to R3. We'll be putting in a capacitor here. So okay, oops. Just a moment. Connect it to our ground. Let's put 10 nanofarad to this one as well. 10 micro rather. 10 microfarad. And connect it to our threshold and trigger. Just a moment. I think I did something wrong here. Let me disconnect this. And let me connect it here. Disconnect here. Because this, I think, this should be connected here to our... And just like before, we need to connect our reset or VCC. Let me just check that out. I think I forgot it. Let me just verify it a moment. Okay, let's try putting in output values for the capacitor. And let's try playing it and see if it would actually work. I kind of forgot. So it's charging. And what would happen is that if it reaches 3.33, it should discharge. It would go. The LED would go down. The green one here. So there we go. And that would also discharge the capacitor. Once it reaches the one third, 1.33, 1.67, it would go back up again, and the cycle continues. So what happens is that we didn't need a switch because what we need is a free running oscillator or square wave generator. Initially, our C1 would be, because discharge is turned off at the first instance, C1 would charge up to two-thirds of the VCC. And while it's doing that, the output is at high. Once it reaches two-thirds or 3.33 volts, discharge would turn on. That means all the contents of C1 would be discharged to the discharge pin slowly. Then that would be the time that the output would be low as well or off. Once it reaches 1.33, it would trigger the discharge to turn off again, and that would mean that C1 would charge voltage once more, up again to 2.33, then go back down, and up. Now, the duration of its turn on state and turn off state actually depends on both R1 and R2 and C1. If we double C1, okay, let's check what happens. Okay, so we have turned it on. Let's stop, try to reset it. Anyway, it's played. Okay, so let's just wait for it for a moment. It is actually rising up slowly. Remember what happened with the monostable multivibrator? The duration is longer for the high state or for the unstable state. So in this case, it actually doubled somehow the stable state. But again, what we need is after this because the state changes from once it reaches the two-thirds, 3.33 and 1.67. So once it reaches 3.33, it would go down. Its discharge rate is almost the same. It will go down to around 1.33 and go back up again. So actually both the duration for the high state and low state actually doubled. And this one would reach another 4.67 or 3.33 volts. How about if we change the ratio? So let's put this at 10. Let's change the ratio of this one 100 because it's half 100k and 50k. Let's see what would happen to the ratio because we want to control the high state and the low state and the ratio or its duty cycle rather. Let's play it again. So just take a look at our output. Okay, so once it reaches 3.33, it would go down. So let's take a look. Its high state is around 1.63 seconds. Its low state is from 1.63 to 2, so around zero point 0.4, 400 milliseconds. Okay, so 1.6 and zero point 0.4, around 1/4. Let's try changing it and reversing this. Changing it to 50. And the other one to 100K. And let's play it again. See the effect. So 1.6 and 400 milliseconds for the low. So we're still waiting for it to rise to 3.33. But technically what's important is the duration from 1.33. So that's how we start, 470. So it's not really 1.6, it's more of 1.2 rather. So it stopped at around same 1.64, and go low at 2.34. So let's wait for the higher state, because remember the ones here, it still included the time for it to reach from 0 to 1.33. But here, it's much shorter. It's already 1.67 rather to 4.33. So we have 2.34 here up to 3.34, almost 1 second. And the duration for 1.6 to 2.7. Okay. So 2.34 to 3.34, approximately 1 second. 3.36 to 4, 600 milliseconds. Okay. So actually changing the lower actually changed or made this longer. We'll learn more of this once we get to the computation. But last thing before we go, one of the things they do physically is, instead of using a, let's go back to schematic, instead of using this, oops, instead of using this, they use a potentiometer for us to be able to control the blinking state. Again, we use the potentiometer, we just use the middle and one of the ends, not both of the ends, because if we use both of them, then we'll just be using the constant. It acts like a fixed resistor. So at 50% it's 10K, or no, its full is 10K, so it's 50%, it's at 5K. Let's have this at 50. And split and play. So right now it's at 50%. Let's play for it with for a while. I can actually control this. So it's still rising. Again, we still need to wait for it up until it reaches 3.33, because this is the initial turn on state. We won't be doing anything. So right now it's at 50 and 25K because it's at 50%. So let's see. So we have here 1 second, so almost 5, so 500 millisecond, and around a turn off time of around 200 milliseconds or 180 milliseconds. So if we switch this to 100%, let's wait for it to turn off again. Because right now it's at 50%, so this is 50, 25, and a 10 microfarad. So let's wait for it to, then I'll switch it to 100%. I switch it to 100%. So right now it's at 50 and 50K. So at this rate, it's almost always turned on. Look, the discharge is quite fast that it almost discharged it instantaneously. So we use this to actually, but the length of it's also affected. 3.4. It's shorter than this one, but it also affected the duration of the discharge. What if we reverse it? We go at 0%. So right now, it has a longer charge time. That means a longer duration for the LED to turn on. And a longer duration for it to turn off as well. At 50%, it was around, so 2.2, where did it go? Oh yeah, 2.2 to 2.38. It's around 180 millisecond. Right now, it's around, at this point, 5.4, 412, 767, 412. So around 350 milliseconds in turn off time. So by attaching a potentiometer here, we can actually control the blink rate of our LED. But we'll have a fixed R1 and a fixed capacitor as well. So if we want to change some of the characteristics more, we have to change this to another level. Anyways, hopefully you learned a lot from how 555 timer works and how to create the three types of multivibrators using our 555 timer. Hopefully you also learned how to use Multisim as a way to simulate different simple circuits that you might have in mind. So all of the laboratory exercises that you might have done or you will be doing can actually be, most of them could be done in Multisim. Of course, there's nothing better than actual live circuit testing. But if for some reason, due to lack of funds or so for anything, could use this. Anyway, thank you very much and have a great day.